So let's start. What we want to do, again, just to quickly iterate, where we ended last time was that we ran a simple example from from the already given DAMASK files. This is what you can easily do to test if DAMASK on your system is working and behaving the way you're expected to, and the example files are running fine, and the example script for post-processing the results are running fine. Today what we want to do is we want to go one step ahead. We want to create our own set of files for a targeted simulation, and then we want to run these simulations. We will still use a lot of data that is already in the DAMASK libraries, but we will try to adopt that for our own case. So for this simulation, what I will call, I will call that single phase sim. Just changing the name. So in this simulation, what I will do is I want to create a file. Um, um, so in this first example, what we will do is we will create a single phase 3D RVE. Then we will create a material file for this geometry, and this will be ferritic steel. Then we want to then we will want to define a load file for monotonic tensile test, and in small strain regimes, and then we will post process the results. And visualize them. Okay, so that is our plan for the first case. I've already created this folder, and what I want to do is, as you remember from the pre-processing and from the previous cases, we want to have three files in this folder: the geometry file, material file, and load file. We want to start from the geometry file. Okay, so what I will do is I will use Dream3D to create this file. There are two ways of doing it. I can also, for example, just use DAMASK initial pre-built libraries to do that. For that, for example, I see that DAMASK, yeah, DAMASK is running. So the way to do that is first we create seeds, then we create the geometry from those seeds. Um, Seeds from random, and then I just define I will just look at help first. And if I look at its help, what I see is that I have to define, yeah, grid, and then the microstructure, no, the number of grains, yeah, number of seed points, right? Um, so to run this, what I have to do is um, size of the grid. will be, let's say, 30, 30, 30. I will keep it, or I want to keep it small. 30, 30, 30, and then the number of seed points will be, let's say, 20. And I want to write this called seed.seed, right? So if I look at this file, there will be 20 seed points that will have their random orientation distribution assigned to them, right? And what you will see is that our grid size is 30 by 30 by 30 in this file, right? And this is the command that we use to create this file. What I can do is then um, I can run this command from Voronoi tessellation, and then I want to use seeds from this file, and I want to export my results to a geometry file, um, and then I can also, for example, then visualize this geometry file. So what is written here? Geom check, and then if I run this, it will create a VTR file that I can then visualize. Let's open a software, ParaView Pen. Um, where is our file? Not here. Here. I can just bring this file in and try to visualize it. Surface, microstructure, and then now you will see this. So it is a 30 by 30 by 30 file, and then you will see 20 grains with random seed points, and from those seed points they have grown into grains. So you will see some grains are smaller, some are bigger, and the idea with this library is that it is automatically um, 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 there is a terminology, I've forgotten the name. For example, so this grain is ending here, it will start from here, and this grain is ending here, it will automatically start from here, and this grain is ending here, it will start from here, right? So yeah, so the geometry is already periodic, right? So this grain is also here, so if you will put another RVE on this side, there will be a continuation of these grains in all these different directions. um, this is what is automatically done here. So we can either create a geometry using just scripts given with DAMASK, or for example we have more sophisticated tools, because the options of creating RVEs with DAMASK are limited. So what we have is we have more sophisticated tools, for example like Dream 3D, that we can use to create geometry files. And now we will try to do that using Dream 3D. First what I have to do is I have to just move it here, and can I run it? Still no. So Dream 3D. Okay, so in Dream 3D, I have already made a complete video about Dream 3D and using it and so on. What I will now do is I will just quickly open a pre-built pipeline to do what I plan to do. So synthetic, I will want to create a single um, phase RVE. Um, the synthetic volume size of my, for example, is still 30, 30, 30. and resolution is 111. So for that, what I will want to do is I will want to have this mean feature size around 567, somewhere here to, yeah, so something like this, 0 0.3, 0.2. Let me fix this to 1. Hmm. Okay, so I will create data. If when the data is created, all this is fine, I will again tick here periodic boundaries. That is basically the grains will be consistent on the boundaries, and then everything else remains the same. I want to create IPF colors from 001, so from Z direction. This is the direction I will be looking at, so let's seems good. Now I want to write a Dream 3D file in my computer. Oh, yeah, here, simulations, and I want to change the name single phase Dream 3D file, and then I also want to export this geometry as a DAMASK file. And I want to export it as grain wise. Output path is again simulations, this one. This is the output path. Geometry is single phase dot geom. I think I do not have to write dot geom here. It will automatically write it here. Homogenization is 1. I have to select feature IDs, Euler angles, and phases objects, and then basically what I can do is I can run this, and what it will do is it will create these files and save them in my folder that I was working in, right? So in this folder now you will see we have this single phase.geom file and Dream 3D file, and also this single phase XDMF file for visualization. What I can do is I can easily visualize what kind of microstructure has what kind of microstructure have I built using Dream 3D. I can close this. It is also 30 by 30 by 30. I want to see the surface. Um, Feature IDs, and then you will see I have this, because here the feature ID was relatively smaller, right? So what you will see is that with Dream 3D we have better control over how we are how we control the number of how we control the feature size, and again you will see that the RVE is periodic in all directions. So this grain is ending here, it is starting here, this grain is ending here, it is starting here, this grain is ending here, it is starting here, and so on. What we can also do is it has exported other attributes to it. So what we can do is we can see what are the IPF colors from the Z direction. So we can see that it has orientation distribution according to the inverse pole figure of um, um, cubic materials, this one, right? And we can see that it is quite random. What I will want to do is I will want to go on and go forward with, for example, this kind of file, because I believe this is what most people will be doing, and this will be a more appropriate example to carry on with. So what I will just very simply do is I will delete the files that we created using the DAMASK script, right? So we have now this single phase.geom file. It has also created this material.config file, right? So what you will see is that in this material.config file, it is mentioned it is generated by Dream 3D. We still have to add homogenization, crystalline, and phase information for complete definition, but the texture information and the phase information should be given here. Texture information and um, microstructure information is given here. And what we see is that there are a total of 111 grains in our representative volume element. Okay, so what we want to do is to complete this material file, we need to add these homogenization, crystalline, and phase information from a file. What I will do is I will quickly copy this information from this material config file to complete that. But then later we will also change something else, right? So what I will do is I will just copy this and paste here. Okay, so now we have homogenization, crystalline, and phase information here. We have discussed this earlier, that homogenization is basically how we divide the total load or deformation on individual solution points. For now, we are not using any type of homogenization here in this simulation. Crystalline basically defines what kind of outputs do we expect to save or record from these simulations. For now, for example, we are just saving everything. Later we can, to save space on the hard disk, we can um, comment out the things that we do not want or need. And then in this phase information, for now, for example, because we have copied it from somewhere, you will see that we have phase information related to aluminum phenomenological power law. Okay, so what we want to do is, because we decided that we will run the simulation for single phase ferritic steel, we need to use properties of steel instead of aluminum. I have this resource here because with DAMASK they provide the um, pre-built pipelines or libraries to um, to pre-build different material configuration files to quickly start with. And for example, here I will be using one for um, ferrite. Uh-huh. The better way of doing it is look at the list, not homogenization. So I need phase information for phenomenological ferrite, right? And this is what I will just copy and paste in my material config file. And here I will just replace this with this. Okay, so you will see that they have used Hooke's elasticity and phenomenological power law plasticity, but it does not have elastic parameters, and I need to define them here. Uh, it is not given here. Yeah, it is not given here, and I have to. Oh no, they're written here, right? So we have elasticity parameters written here, and then there are some plasticity parameters for the phenomenological power law that are mentioned here below. Okay, so with this we have our material configuration file ready. What we want to do next is we want to define our load file, and for that as well what I will just do is I will copy the load file and just modify it a little, right? So initially, for example, we are defining load of this is deformation rate 180 terraced per minus 3 seems reasonable. We are applying this for 10 seconds and in 40 increments, and with 4 frequency we are storing it. And in the next one we are defining this for time 60 because I want to run it for smaller strains. What I will do is I will do it 50 in 100 increments, and then no, yeah, and then do the same here with frequency of 10, let's say. Okay, so what we are doing here is we have divided the low step in multiple steps, and we are just running the simulation for total time of 110 seconds with this deformation rate, and you can then multiply this to find out what will be the total amount of deformation in our RVE. And this is it. I want to save this, and now when we have this, what we can do is we can open terminal and run DAMASK simulation. Wait, what I want to do is I want to GitHub. It is not signed in. I somehow want to import a script here. Hmm. Because that will make things much easier. Well, we will import the script in the next step. So what I want to do here is I want to um, run the simulation. Open in terminal and DAMASK spectral. Load file is tx.load. Geometry file is, the name of the geometry file is single phase.geom, and I run this simulation. Okay, it will take some time for 240 increments to run, and in the meantime what I can do is I can try to find the GitHub files that we want to use. Hmm. github.com //damask. Oh yeah, we can open this. So if you will go here, we have these different scripts written here. So what I will just do is I will try to download this script, right? And I will also sim automate and output automate. I will also try to download this script. There is a very small difference between them, but what I want to do is I want to copy them to my simulations directory, and we will see what is here. While this simulation is running, right, we can take a, oh, it is taking time. Even 30 by 30 by 30 is slow. Okay, and I think we have selected less number of processors that are being used to run simulation. Probably that is why it is also taking longer. But let's see what we have in these scripts, and maybe we will run the simulation again. So I will open this. In this script, what we are doing is that it is a bash script, so it will run these commands one by one itself. What we are doing here is first we are exporting DAMASK number of threads equal to 8, right? In the case of, for example, this computer, when we have 30 by 30 by 30, I think 5 should work fine. Or so if I have 30 by 30 by 30, this is the total number of divided by 8 is okay. 8 is a whole number, so we do this. Then we select a geometry file, then we select a load file, and then this is where, for example, where I define which increments do I want to export the results for.
For each increment, we'll get the result.
We can, if you want to, because this command will run in loop. What it does is that it asks me for the first increment, the last increment, and the step increment. This is what we do in this area here. But the important thing is that it runs this simulation on the selected load file or geometry file, and then it automatically post-processes the results. Now we only have CRFP, we do not have this exported in the current case, so I will delete this, then everything is fine, and these lines will not be executed, so I will just delete them, and then it creates a copy of the results, and in these then it cleans up to just write Mises stress, Mises strain, and that's it, right? So previously we saw that how do we run all these commands one by one, and what are the implications. So what do these commands do, what do they write in the file, and then we were able to reach these Mises stress or strains. But what we can do is we can write a script that will automatically do this on all the files later. And similarly, to look at the local results, we have already this this command written here. What we can do is we can clean this up as well to run this script. I do not have this, I do not have this. Yeah, and then we have this grid, it adds all this, not this, and the I am it is not calculating. It is not calculating this, so I will just remove this. Okay, so you can read this script yourself, but the basic idea is that these are all the commands that we run manually to run the simulation, to post process the results globally and locally. But what I did in the past was I created these scripts to do it automatically step by step, and this is what I want to use in this case now, right? I just have to quickly, so we see that the simulations are running quite slow. I will close this. um, I just have to see if this is executable. No. So we see that SimAutomat is not executable right now. U plus X SimAutomat. And now we see that SimAutomat is executable. I can now run this and it will ask me what was your first increment. So I know my last increment is 240. So I will just write here 240, 241. And then now it will run the same simulation again, but but now because our default number of processors is that the computer uses is 2, and now we have manually selected it to be 8. Hopefully the simulations will run a little bit faster, and once the simulations will be complete, we will automatically be able to post process our results globally and locally, and then we will see the results. And that is how we do not have to um, manually do things multiple times again. This is also important. You can generate or create these kind of scripts for your own cases or simulations. It is also quite easy to do, and especially in case of Linux, you can create these kind of scripts when you exactly know I have the same geometry file with the same um, name or syntax, and I always run simulations first, then I post process my results in this way, and I'm always interested in looking at results from this side, and my scales are these. You can also combine, for example, I've not done this here because I run less simulations, and and I manually post process the results every time. But for example, you can also continue to write the script for ParaView visualizations. So you can import this file in ParaView, you can control everything, and you can directly export images in your folder um, from the ParaView visualization that you can just quickly see as JPEG files. You will not even have to open ParaView as well. So the idea is that if you have a certain list of simulations that you want to do, by systematically changing something in it, you can create scripts like these to make your work much easier and much faster, and also more reliable and repeatable. So all the simulations will go through the same process, and it will be very easy to see um, or make changes to almost all of them instantaneously. Okay, um, and yeah, so the simulations are running, and while they are running, what we can do is we can create another um, set of um files for our next case that we want to talk about today. Okay, and the next case that we want to talk about today is um, multi-phase. Okay, and in this case, what I basically want to do is I want to change two things. In this first case, we just had ferrite matrix, or all the grains were just one single material, ferrite. In the second case, I want to copy this file and I want to manually change some of these grains to, let's say, martensite. Okay, just to give you an idea, to repeat what we discussed in the past, how DAMASK reads files and information, and then how we can alter these files. Um, and then the next thing what I want to do is I want to, then of course I will have to change the material file a little bit to define the properties of another phase, and that's what we will do. And then the third thing that I want to do is, instead of applying tension in the x direction, we want to apply compression in the y direction, right? So instead of applying tension in this direction, we will just apply compression in the y direction. And later, we want to compare results of these two simulations side by side to see what are the similarities, what are the differences, and and so on. Okay. So to start with that, what I will do is I will just copy those initial three files from this folder. So geometry file, load file, material config file, right? And I will also copy this about.txt file to then write what we will be doing here, right? So in this file, create a two-phase 3D RVE, um, ferrite plus martensite. Okay. Create a material file for this geometry. Now ferrite phase plus elastic martensite. So or ferrite phase plus martensite phase. Okay. And then we want to define a load file for monotonic um, compressive test in again small strain regimes, and post-process the results and visualize them. That is what we want to do. And another thing that we want to do is we want to run simulations using, that is what we have done with the other one, but using bash scripts. That is what we want to do here. Okay, let's go into the geometry file. So what we see here is that we have grid of 30 by 30 by 30, and then we have certain grains with certain addresses, right? We randomly want to define some of these grains as martensite instead of ferrite. We want to keep the size similar, we want to keep the grain structure and their orientation similar, so later we will be able to directly compare the results, right? And therefore we do not change anything in this geometry file. What we do is, however, we go into this material configuration file, and this is where we will want to make a lot of changes. So the texture will remain the same for all the grains. We do not want to make any changes here. But for example, here in this case, when we see, for example, there is a certain grain one, right? And it has phase one and texture one. We do not want to play with the texture, but we maybe want to say it has now phase two. And similarly, randomly we change some things here, right? The idea is I'm just trying to randomly do this when we have actual geometries, when we have
What about the volume fraction? The phase volume fraction?
of course it will depend on what
How
will
much
be the
material
size of
you
the
need?
grain
Okay.
that I'm playing with. That is why I'm blindly doing it. I'm just randomly doing it. I have no information about that. But later, when we have actual materials, when we have their volume fractions, we do not do it like this. We use, for example, a software like Dream 3D to artificially create exact grain sizes and grain proportions and their positions that match with our material um, microstructure, right? But here I'm just trying to recreate this example with another phase, and I'm just randomly assigning them different values, right? And then, for example, I will go here, I will just define this too and this too, saving this. And okay, one more thing that I should have done in the material config file is, because now I have said that some grains have phase 2, right? But if I go in my description of phase, I only have this one phase defined. There is no other phase defined, so I have to define my second phase here, right? So those grains could be assigned then second phase. What I will do again is I will go to my um, DAMASK library to see if they already have martensite material properties that I can just copy and paste here. Um, um, phase, pheno, so here, right? And I will just copy this and paste here. Okay, so now I have this one phase. So this is whatever is defined on top is phase one. Whatever is defined second is phase two, right? And whatever defined in the third place is phase three. There is no way of telling it. So this is phase two or this is phase one. You have to keep one on the top and one the other one at the bottom. So now I have modified my material config file according to what I expected. Then what I also want to do is I want to apply compression in the y direction. Okay. To do that, imagine this is a matrix, right? So it has 3 by 3 components, 9, yeah, so 9 um, tensor components, and what I want to do is I want to define this as static, and this oh, I should have copied that, and I want to define y as this. Okay, and z is still open, so it will deform to any value that I want. Now what I need to change is, instead of stress being unidentified, in this case I have to define this as 0 and this as static. Okay, so I adjust my boundary conditions accordingly, and now what I have to do is I just copy this for all the rest of the cases, and this is the kind of load that will be applied. Oh no, this is the kind of load that will be applied in all steps. Okay, let's see if the simulation is completed. Okay, so what you will see is that the simulation completed, right? Then it post-processed the global results, then it post-processed the local results, and in the end it wrote everything. So I did not have to worry about writing all the individual commands in. We can quickly go and see the results of the single phase. The results will be in the post-prog. First we have this clean file. What we see is that we have the mesos stress starting from almost 0, reaching up to 467 megapascals, with mesos strain in percent reaching up to 10.4%, and the total number of increments for 240. This is the last increment that we have extracted, right? And we can visualize this. So this is the VTR file for this frame. What we can do is we can visualize this. So this was our initial um, microstructure, and now we have this file that we can visualize. And you will see that I exported a lot of variables that I do not really require. If I just click on mesos stress, what I see is that this is the stress distribution, and if I just look at mesos strain, I see that this is the strain distribution in my sample or material. There should be a separate lecture or talk on specifically on ParaView and how to use that to post process and get interesting, useful um, images and figures out of this, and how to do that. We will do something later, but for example, you can very quickly see this scale and then these results, that these dark blue points correspond to very low strain value, and then these red points correspond to relatively higher strain value, right? And if I
So one more
correspond,
thing, the simulations ends when the material yields or depends on simulation timing.
depends on the simulation time. So simulation ends when either your completion time ends or when it runs into an error, right? That it was not able to converge, right? And it finished here because I just told it to run for 240 increments and this much strain, and okay. So while we are looking at the results, what I will want to do is I will want to run the other simulation of multiphase material that we just defined. Um, and oh, I do not have the sim automate file here. I will just quickly copy it from I cannot. Home DAMASK simulations single phase, and then the name was sim automate to here. Okay, so we have this file here now. I can run this simulation using this. I will again write 240, 241, and the simulation will run again. Okay. So while this is running, we can try to look at some results in more detail. What I can do is representation, edit color, and yeah, can go crazy about it. So instead of using this, what we usually do is we use this. And then instead of defining zero point 0.2 rescale, so what we see is that this grain has significantly higher strain as compared to, for example, this grain and the other grain, and this is how we can just decipher the results. Um, what we also want to do is, for example, we can see what texture they have, right? So this is a different grain, this is a different grain, this is a different grain, and this is a different grain. And then, for example, if I look at its mesus strain, what I do see is, again, it will be refreshed. I have to adjust it again, but what we see is that this grain has relatively low strain as compared to the other ones. But if this grain has lower strain, this would mean it would have higher stress. Hmm. Relatively more, but not that much. Here and somewhere here. What I can do is oh, it inverts. No, I don't want to do that. What I can do is I can just choose this and then, for example, define it manually. So from 0 to this is 953 megapascals. I can define 800 megapascals. 8 E8. This is too much. This is better. Okay, so then we see the stress distribution in our microstructure as well, right? What you will see is that the distribution is relatively more diffused. So we will see some grains have higher stresses, whereas the other grains have lower stresses, but then there is a gradient between them. This is something that we will clearly see not happening in case of the other um, simulation case that we will see later. Um, so the idea of showing you these examples or going through them is to give you a little bit of background about um, how from the basic um, idea of what kind of simulation I want to run, I build on the cases that I can quickly simulate to reach the closer results. Of course, if I have to do more precise calculations, what I do is I need to define more realistic loading states. I need to define more realistic material parameters. Um, and that itself is a huge science on how to identify those parameters. And then I also have to define my geometry and microstructural configurations quite close to um, what I actually see in my material and so on, right? But this is always a nice starting point to start from very basic simulations, very small ones, to at least um, run and see if things are working fine, and then slowly fine tuning them. For example, if initially first playing with the geometry file and fixing that, then maybe controlling the load file and then fixing that, and then in the end going towards the material file and playing with the parameters to fix them with with what I want to exactly reach later for my material in my case. And once everything is fixed, the workflow is still the same. So we define these three files, we run the simulations, we post process the global and local results, we look at the local results to see which point we have reached, and then compare this with where we actually want to go and see if we are already there or we need to make some adjustments in the files. Then we do that, follow the same pipeline again, reach that, and then again recalibrate and reiterate on that. Okay.
Yeah. So one more thing. If you take a RV sample size of 30, 30, 35, and
Mm.
300, 350, will the simulation results which will come while doing this will be different or will be the same? If we change only dimension.
This is um, uh, okay. This is a very good question. DAMAS does not have any idea about dimensions.
Okay.
Okay.
Just number of grains and number of
It is
features.
just the number of grains and the number of grid points it has to solve
Yeah,
every
grade,
time.
grind, load and so on.
Right. So if the number of grains and their shapes and their volume percent remains the same, but we just increase the resolution, right? So instead of 30 by 30 by 30, we define, for example, 100 by 100 by 100 or 300 by 300 by 300. Ideally, the global response, the stress strain response on average will not change for the material. But of course, the local response for one pixel, maybe when there was very high stress at one point, now when it is relatively away from the grain boundary, there the stresses might change there. So the local results probably do change, right? This is what we have observed in the past with 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 all the simulations and all the cases, but the global results do not change. So it is always a question, and then there is also a limit on the resolution. So just like mesh dependency, if we refine the mesh size to more than a certain extent, then they also stop changing. So they do not change after that at all. And the then the question always is, what kind of results are you more interested in? If you're interested in the local results, it is always a good idea to define a better resolved geometry, right? So which has more detailed grains, and you can and the results are locally resolved, um, and then you will be able to see what is happening inside the material. But if you're only interested in the global results, then what I always do is I define a very rough geometry of very small size, so I can run very fast simulations and at least quickly get the global results that I can then use to see, or for example compare or calibrate. And then we have techniques, for example the minimum size of the geometry, minimum number of grains that are required to at least reach that isotropic level of that as well. Hmm? So to summarize, by improving the resolution, probably the global results will not change that much, but the local results will. So depending on what you are more interested in, you might need to adjust this according to your requirements. And the simulations are about to finish. But the good thing about this is that, but the good thing about the script is that it automatically runs and post-process the results. I remember the time when I had to do all this manually multiple times, and I used to make one mistake, and after 15 lines of commands, I came to realize, oh, the variable name was different, and I cannot see them, and I had to redo all those 15 commands again. But yeah. And then, for example, you can also use these scripts in different configurations. Now, for example, if I have one folder, in which I have 15 folders containing individual files that I need to run simulations on, I just need to run one script to say go into each folder, run a simulation, post-process the results, and then continue to do that until you've run simulations in all the folders, right? Or I need to post-process results for all these folders, for example, for a specific frame, and for a specific variable, just do that, and it does that as well. So it just depends on the use case that how you build that. The important thing is if your fundamentals are correct, if you understand things fundamentally, you're able to build your simulations. Um, the next task of repetitive simulations and post-processing the results becomes much easier. You do not have to do that a lot. Okay. And what we see here is that it will take almost 1 minute each to write this. And then we will have our results here. We already have our global results. We can look at them. And then we will see that for the same 240 increments, we are at almost same strain. Previously it was 10.4, now it is 11.6. Um, but the stress is much higher, right? Because now we have, so instead of 420 or 400, it is now 550, somewhere there, megapascals. And that is because now we have some grains of martensite, which is a very strong phase, and therefore we have significantly higher stress, right? So you see that we did not change any orientation of the material. We did not change. Also, what something that we did was we applied compressive load instead of tensile load, and therefore you see a small difference in the amount of strain that happened in the material because different slip systems activated. If probably I ran it on tension, it would be extremely close to 10.4, somewhere there, right? Um, but yeah, you see the global results, and then I think, yeah, so the local results have also processed, and we can see that. And what I will do is I will quickly import this file here. Okay, just to give you an idea, what I can do is I can create a render view, I can see this surface stress, and what I can do is link camera to this. Okay. Oh, okay. And now what you will see is that we have stress, but I have to modify this edit color, and I want to define from 0 to, it is 4 megapascal. 4, 1, 2, 3, 4, 5, 6, 4 GPa. Really? So previously we set the limit to 900 MPa. That is what I will do here. 9E8 rescale. Oh yeah. Okay. You see, right? So there are some grains that are martensite, and what we see is that the stress in them is extremely high, right? And and then, for example, when we compare the results with the previous one, so this is one grain, this is also the same grain, but now the stresses are a little bit higher because it is very close to a martensitic grain here, and similarly the stresses here are very small, but now the material is the material is quite close to a martensitic grain, and therefore the stresses are relatively higher here as well, right? This is what we see here, and similarly, for example, it will be quite nice to see. So this area here was relatively relaxed, but now it has significantly higher stress, and now the lower stress is distributed here, which was relatively at higher stress earlier, right? So martensite has taken up a lot of stress in this strain regime, up to 10-11% of this, and we can also do that, for example, for strain, and I can change it to strain. And then, for example, we can see that in martensite grains we have almost no strain, almost zero, and on the grain boundaries we see a very high strain value on the interfaces, and similarly here, right? So we can compare these two um, RVE side by side. In one we have few martensitic grains, in the other we don't have anything, and we can see the similarities and the differences in the results. Um, and also we looked at the global results. We can also, for example, just use any plotting software, Excel, MATLAB, Matplotlib, Python libraries, or whatever, to compare the overall stress strain curves, and we will see that there will be significantly higher hardening in case of dual phase steel as compared to single phase steel, right? So yeah, this is generally what we wanted to cover today. And I think from this point onwards, if I say, for example, run a simulation for, let's say, um, magnesium, right? So you will automatically be able to create a geometry file using Dream 3D after watching the video of single phase magnesium, then pick up the library of magnesium from there, pick up the default load file, and at least run the first simulation to see what results are you getting, right? And then the idea always is to, for example, say, okay, we want to see how much twinning is happening in the material, and then from there the points diverge that for now we have not exported that result, we have not looked into it, but then you will be doing it, and it is just seeing, okay, I have to export this variable, I have to write it in my files, and later I will be able to visualize it. And for example, in your case, when you'll be working on
Aluminum oxide
aluminum oxide and niobium, you know that you have two phases, they have certain composition, you will be able to construct um, an RVE out of that. You will be able to see which libraries are closer to that, which crystal structures or which materials are closer to that. You will be able to pick that up, and then of course modify all the parameters. We will do that together to modify all the parameters, and then reach your results with the specific load file, and at least run the initial simulations to see what you're getting, and then see where we actually want to go and what are the differences there. Okay, so I hope that after this you will be able to somehow have DAMASK run initial simulations, um, and get some results, and probably while doing this you will have a lot of questions that you will write down, and then in And then I know that later we will also have to discuss peer review, how to extract meaningful results from here, how to export all the pictures in high quality to be used later. We will do that later, but also, for example, global results, different variables and values, and how to write them, how to calibrate the material libraries, how to export them. But let's first run the initial simulations. You will have a lot of questions, and then later we will have more sessions to talk about these things. Okay, so yeah.